Thanks for being here. This is a mini course about categorical probability. Hopefully by the end we'll have an idea like what that means. I mean, it could mean different things to different people. And it's very fitting that I can talk about it here at Perimeter because, I mean, here down you can see a list of people that I have been collaborating. Some I have not personally collaborated with, but what I'll be telling about is also their contributions. And the first one on the list is Tobias Fritz, who have been a postdoc at Perimeter, and actually a lot of the ideas that I will be talking about come from the time when he was also based here, and I was here as a PhD student before master student, and so that's kind of the connection how I got in touch with these ideas and this work, and it's really nice to be back to kind of present what has happened. I mean, Tobias's paper, which started a lot of these developments, comes from 2019, so that's now 6 years ago. And during these 6 years, there have been a lot of developments, a lot of new ideas came to light. So I hope to give a kind of overview of what we have been interested in and maybe where that goes. Maybe before we kind of delve into our approach, a little bit about the background or like the history. So I think in probability theory, if you look at some like works of Kolmogorov already from like the early 20th century, you may find like from our like modern perspective that some results like the Kolmogorov extension theorem, which is about like the structure of measures on like an infinite product of sample spaces. Actually, what he showed in that theorem is what we would now call a universal property in category theory. But this was before even the first definition of a category appeared. And so that's just to say that somehow in the kind of very basic workings of how we think about probability measures and probability theory, there are some like hidden like structural pieces, and what we want to use category theory for is to extract these structural pieces and maybe therefore understand probability theory better, and maybe also be able to kind of reason about uncertainty in a way that is not so wedded to a particular model of how we think of uncertainty, but rather using these structural properties. And with yeah, of course.
So this thing you call the Kolmogorov extension,
yes,
is that the same thing as the Chapman-Kolmogorov equation?
No, it's different, but I will get to that probably in the third lecture.
Third?
Yeah, so,
Thank you.
yeah. So with that in mind, I want to take a kind of road towards our framework that doesn't start from category theory, because I don't assume that you are experts on category theory, even though some might have seen some of these concepts and also worked with them. Rather, I want to use a particular like language that we can use for our framework, which is in terms of diagrams. And so we start from the diagrams, we try to understand what these diagrams mean, and we will use them as a kind of gateway into the framework, and to be able to understand what are the elements of the framework and what we can and what we also cannot do with it, because it is a framework that has some advantages, but it also has some limitations. There are some things that like inherently are not part of the language. And by the way, of course, like at any point, if you have questions, then please stop me and we can discuss. So let's look at one of the starting points of the diagrammatic language, or kind of very like basic elements, is the idea of conditional independence. I guess there are many reasons why conditional independence is relevant, but one importance of it comes in the context of causal inference. So if we think of Reichenbach's principle, which I don't want to go into the details of right now, but one of the consequences of this principle is that if we have a situation where there are events A and B and C, and indeed the event C is a complete common cause of A and B, then we should expect when we collect data about the values, like joint values of these events, that in the data we should see this fact as the presence of some conditional independence, that indeed when we condition on the particular value of C, then A and B become independent. Or in other words, if you want, if we express it in terms of the standard probabilistic language, this statement would say that if we want to know the probability of event A, then we don't need to know both B and C. It suffices to know C. And so once we know C, B becomes irrelevant for learning about A, and also vice versa. Okay, so that's kind of the standard like probabilistic expression of conditional independence. And the way that we get into the diagrams is that we try to express this fact about somehow A and B being only dependent on C in terms of a particular diagram equation. So I don't expect you to kind of know everything like what this means, but just to give you kind of like a visual representation, we can kind of decompose a diagram in this way where there's like some middle node on C, and B and A are kind of connected to C. And this kind of structural kind of diagrammatic decomposition expresses the conditional independence. But now I will go into the details of what these diagrams actually mean. And maybe in order to give you like even more like motivations, like of course one motivation that I just presented is that we want to be able to we want to develop this framework in order to have some kind of diagrammatic language to talk about probabilistic processes, which maybe has some intuitive elements, like it can express these conditional independence relations, but at the same time is also formal, so it's grounded in some formal mathematical theory. But that's just one of the motivations that we have for all this work that we do. One other motivation, which I also mentioned a little bit, is that we can, at least we hope, to be able to reason in a model agnostic way. So that means maybe we want to reason about uncertainty, but we actually are ourselves uncertain about how to express this uncertainty. So maybe this uncertainty can be expressed using numbers like probabilities, but maybe that model of probability turns out not to be the correct one in the future, and actually a better model would be using something like quantum theory, or using possibilities, or using imprecise probabilities. There's different ways to model uncertainty, and like one of the motivations of using the structural properties is that we can make reasoning that are somehow independent to some degree from this model. One other motivation, the third one on the list, it relates to the fact that we, rather than specifying the details of the situation in terms of some topology and some spaces that we work with, we rather use arguments that are based on some axioms, and these axioms can be used as long as the actual model that we might imagine is describing the situation satisfies the axioms. But we don't need to work with the details of the model, just with the axioms. And this gives us kind of a way to see proofs as patchwork, a build-up of like smaller like ingredients that are like abstract reasoning.
Were you saying that was
Yeah.
in contrast to topological reasoning or similar to?
It's actually I would say in every domain of mathematics you can have like this dual perspective. You can like reason in terms of the structural properties of your mathematical structure, or you can reason in terms of something like the details of your model. Like, so rather starting from the model and what are the properties of this particular model, like I'm using like real numbers and I use all the properties that it has, or I rather use just the fact that real numbers are like a field and maybe an ordered field or something like that.
So you think topological is not a synthetic approach? Is that how?
Generally, is not. Yeah, but you can have algebraic topology, which maybe is more synthetic. So there are different approaches also in that space. Yeah. One thing that I will not get into in these lectures is the fact that people are also interested in categorical probability because it can give us a way to talk about programming languages which are natively probabilistic and involve conditioning and Bayesian updating and so on. Yeah, we will not get into that, but that's one of the connections that this work has to computer science. And one of the kind of motivations from the mathematical side is that by expressing facts and results about probability theory in this abstract language, we can hope to generalize them to new situations. This has been successful to a little degree. I don't think we, so far in these last 6 years, have been able to deliver like a proper, like really interesting generalization that would be unknown before. But there are some small hints that there are definitely new results that we have been able to show that were not known. But often I think the reason is that people have not asked this particular question because, if you use with different frameworks, different questions become more natural. But that's Rob.
Just before we move on, I want to get clear on this synthetic approach versus, I guess, the counterpart would be like an analytic approach to mathematical topics. Could you take us through that in the context of, say, geometry? Like, what would be characteristic of the synthetic approach to geometry versus the analytic approach, just so that we sort of are in the right frame of mind?
Right. So in the context of geometry, you can think of the analytic approach as being something like differential geometry. So we specify like a concrete charts and an atlas for our differential manifold and the way to kind of transform the transformation rules between like different patches, different charts, and then we can differentiate and we can look at like the structure of these spaces, and then we extract properties about this manifold from that concrete kind of picture. And I guess the synthetic approach could be something like we rather look at what are like more like global properties of these spaces that we are looking at. So maybe we try to derive like kind of results about the geometry of the space just from some basic principles. Like maybe we know that it's simply connected, or it has a particular like topological structure of the paths and higher order paths. And so in this way we can extract features of the geometry without knowing precisely a precise kind of concrete embedding of it in, or something like that.
And if to use a simpler example, like if I do a proof using Euclid's axioms versus using algebra and like Cartesian coordinates, that's a synthetic versus analytic.
Yeah, I would say so. Yeah, indeed. Yeah.
Okay.
Yeah, I think, in these lectures, it will not always be like so present, this motivation, but it is a little bit in the background of what we are trying to do. Yeah. Okay. So in order to kind of move into this diagrammatic language, I chose to look at a particular example of a result in classical probability theory and try to express it. So let's look at Bayes' theorem. So in standard probability, one of the ways to express Bayes' theorem is that the joint probability of two events can be computed by looking at the marginal probability of one of them and the conditional probability of B given A. Or in other words, we can compute the conditional probability by dividing the joint and the marginal. Then there is a similar way that we could express this in measure theoretic probability. So if we have, similarly like here, like A and B are two measurable spaces with their sigma algebras, and S and T are particular measurable sets in the sigma algebra, then the probability of the joint event of S and T can be computed by looking at the marginal on A, so that's here, and then multiplying by the conditional probability. And this conditional probability is also called the regular conditional probability in measure theory. We don't have to go into like the details of this, but I think I just want to say that there are in different like mathematical languages, these statements can look a bit different. So Q, so this is just the notation for the conditional, the regular conditional.
Oh, given A?
Given A, indeed, yeah. So when we move to the categorical picture, then we would like to see these different instantiations as somehow expressions of the same result in different, what we call Markov categories. So Markov category is going to be some mathematical structure, a category with some properties, and by picking a specific Markov category, so in this case, one we called thin stock, we recover this result. And by picking another Markov category, we recover the other one. And by picking a completely different Markov category, maybe then it looks even different. But then when we look at the diagrams, we call them the string diagrams because they're like boxes connected by strings. Then the statement of Bayes' theorem looks like this. So again, we have some decomposition. We have some joint that decomposes in a certain way. And now, okay, let's go on and actually understand these diagrams, if you have no questions on this. So the first element that we have seen is a state in a Markov category. So can someone tell me what should a state in a Markov category correspond to in like discrete probability theory? What would that be? Sorry?
A probability?
Yeah, it is going to be a probability distribution. So there is some discrete sample space A, so just a set in this case, and we specify a probability for each element of that set. And in measure theory, this would be just a probability measure. So we have some sigma algebra, and then we specify a probability for each measurable set such that, yeah, we have the sigma additivity or countable additivity, and the measure is normalized to 1.
So are you thinking of the A as a space or as a random variable? Or is there some...
It's a good question. In these examples, they are spaces, right? So in particular, in the discrete case, it's just a set of possible outcomes. In the continuous case, it's basically the sigma algebra of possible events. But these are just two Markov categories, and so that doesn't mean that there are not other Markov categories where it could be interpreted as a random variable. But the ones that we look at are rather spaces, yeah.
And Markov categories are symmetric monoidal categories, right?
Indeed. Yes, I will get to that.
I can think of the A as just the object in the category, R is the morphism, and then it'll have these particular concrete representations.
Yes. Yep. We will.
With another property, or that they're exactly...
We are getting there.
Okay.
Yeah. So then when we look at a triangle with two wires coming out of it, then that's called the joint state. And indeed, in probabilistic language, that we just joint probability distribution. So we have now two sample spaces and the joint probability for joint events in these two sample spaces, which are exclusive events. When we add this black dot on one of the wires, then what we get is a marginal state. So on the right-hand side, we have a joint state Q, and then we marginalize on one of the outputs, so to say, to get just a state on A. And so in probabilistic language, we could say that to compute the probability of the marginal probability on A, we can look at the joint probability and then just sum over all the possible outcomes of B. So this would be the way to express this equation. Basically, the diagrammatic equation corresponds to this one in discrete probability. In measure theoretic language, it looks kind of superficially different, but basically what you have to realize is that this B, this is just the event that corresponds to that anything happens, just like the event of all possible outcomes here. And so then when to marginalize this measure, we just look at the cylindrical set, basically, where there is an event on A that's, and this is a typo, this should be a sigma algebra of A. And then we consider anything that can happen on B.
Sorry, in the previous slide, just a second. There. So could it be that so going back to one of the previous questions, that maybe you're overloading a little bit the notation, say,
Could be,
for
yeah.
capital A.
Yeah.
So if you say when that little a belongs to A, you're thinking about capital A as a state space. And then when you say capital A equals to lowercase a, you're saying that capital A is a random variable.
Yes, indeed. So I think this is kind of the common notation in discrete probability to think of like A as a random variable that has a particular value. And you could think of the random variable that's the identity on the sample space, basically. Like if we consider random variables that are not necessarily real valued, but yeah, just somehow valued in A, then that would be kind of the correct way to think of the notation. But yes, I'm kind of overloading it. Yeah. And I think this is something that, yeah, anyway, like I think it's it should be clear. And actually, so to kind of comment on that, that's I think why at some point I will change the notation, and yeah, rather than writing A equals A, we just look at the probability of a given outcome in the set. And even this notation of using P for the probability, I think at some point becomes confusing when we consider different probability measures on the same space. And so then we could say rather R of A, just like here, and Q of AB. And I think then the notation is a bit clearer. Yeah. Okay. One other concept that we can express is the idea of independence. So independence in the diagrammatic language is, again, like we have a joint state that splits as two states, one on A and one on B, which are basically disconnected from each other. Okay, so this connection corresponds to independence. And what does it mean in the discrete probability? Can someone tell me what is this equation in discrete probability, independence?
Factorization of the probability.
Yeah, so the joint probability splits into a product. So the P of AB is just probability of an event in A times probability of event in B, and is the same in measure theory as well. It's just factorization. Now this is the case of no correlation, so independence, but we can also express the other extreme, the perfect correlation. So perfect correlation, like rather than splitting, we have this dot with one input and two outputs. And if we look at a diagram that looks like this, and it expresses that there is a perfect correlation between the two outputs, A and A in this case. So in discrete probability, that just means that there is a perfect correlation. That means the only joint outcomes that are possible are those where they are actually the same on both of the sample spaces. That's why we have the delta function here. And in measure theoretic probability, this, if you want, we can talk about this, but basically when I look at like a rectangular event, so like an independent event, then I just compute the measure of the intersection between the two individual sets. And actually, if you, that corresponds to the delta function. If, for example, these are just singleton sets in the discrete case, then I get the intersection is non-empty if the two single elements are the same, and it's empty if they are different. So that gives you the delta function. Any questions? Okay, let's move on. I think so. This was about states. So we were always looking at diagrams where there are no like global inputs, only outputs. But we can also consider some inputs, and then we get the idea, which, or the concept in category theory, which is the central kind of piece of the structure, which is the morphism. A morphism in the diagrammatic language is a box with input and output A, output B. And in the discrete probability theory, this is going to be just a stochastic matrix, so basically conditional probability, or you could think of it as a parametrized probability distribution. So it's a probability distribution on B, which has additional parameter in A. And so for each input in A, and we obtain a probability distribution over B. That's a stochastic matrix. And very similarly, just with some additional technical requirements, in the continuous case, we have the idea of a Markov kernel. So a Markov kernel is basically parameterized probability measure. And so for each element in the input space, so little a, and each measurable set in the output sigma algebra, we get a number. This number is then the conditional probability of the event T given input A, in such a way that, for each input we get a probability measure on the output, and also so that the map for each possible event of B, this map is measurable. And so this kind of ensures that the measurability of the input is kind of preserved by the map.
Is that the same as saying you can think of A as distributed?
Yes.
You can sum over it, measurable and...
Yeah, I mean, you can compose them basically, and it makes sense because then you can integrate it. Yeah. Mm-hmm. So that's relevant for the composition then, which we will get to.
We're just looking at wondering about direct delta functions. Are they part of Markov kernels, or are they part of
yes,
a Markov category there?
Yes.
Okay.
This I will talk about also in the third lecture, I think, depending on timing. But there is a kind of, we have a categorical way to express that the Markov category has delta functions, basically. So it will not be the case in general, but with some additional properties, we can say that, so special kind of morphism, which we denote usually not by a box, but just like a single wire without a box, is the identity. And so this is usually required in the definition of any category that we have identities. And identity in discrete probability is just the identity function as seen as a stochastic matrix. And in the case of the, it always goes first. In the case of the Markov kernels, it's very much the same, where we have probability 1 if the input kind of lands in the output event, and probability 0 if the input and output are have zero intersection, basically, empty intersection.
Have you ever encountered Topoi?
Yeah.
Would you say a Markov category is related to Topoi?
I mean,
Topoi is about the existence of these things, right?
There's a bit more.
Okay.
When you talk about topos, then you also need additional properties. There is a relation, which is that's often the case when you look at a category and you look at particular kind of functors out of the category. Then under some assumptions you will get a topos. And so it's very similar for Markov categories. Some people have been studying them very recently, and it's still kind of ongoing, where you look at ways to map morphisms of the category to basically spaces of random variables. You look at and then that gives you a topos. So then you can think of a topos of random variables over a Markov category.
Okay, so
I will not be talking about that, but that's indeed one connection.
is part of what you said.
Yeah.
So Topoi are Markov categories with more structure?
They are not necessarily Markov categories.
Okay.
Yeah.
Okay.
That is more like a construction. You can take a Markov category and look at these spaces of random variables, and under some assumptions on the original Markov category, you will get a topos of random variables. But it will no longer be Markov categories.
So there's no containment.
No.
Thank you.
Yeah. Okay, one other element of the diagrams that we've already seen is this dot. So that was in the context of marginalization. And we call this is also a morphism where the input is A. We don't have any output, but that just means that the output is what we call the unit, I. And this discarding morphism, we can think of it, okay, so in the discrete case, and also in the measure theory, the unit, the output is just a singleton element, so like a trivial sample space. And the discarding map just gives us probability 1 for any input. So it just kind of checks that the system is there, basically. And very similarly for the measure theoretic case. So that's discarding. That's like a very kind of central piece of structure of Markov category. But even more central is the copying. So we have also seen that already. That's a morphism that has one input and two outputs of the same type. And it kind of corresponds to the idea that basically in classical probability theory, or in general when we talk about somehow information, classical information, then we can copy the information, right? So I mean, here often people, or all of us probably think about quantum information at some point, and there we know that we cannot copy quantum information, but a very basic property of classical information is that it can be copied. So this copying morphism in the discrete case, it just gives us probability 1 whenever the input and both the outputs are identical, and 0 otherwise. And very similar for the measure theoretic case, where if the input is included in both the output events, then we get probability 1, otherwise it's probability 0.
The representation of copying as the dot like this, are you assuming that it's related to the discarding and something else, or it's...
Yes. So the copying and discarding together, they have some compatibility conditions. Yeah. And so in that sense, we can see them as like a single structure that plays nicely with each other.
Okay.
Yeah. Mm-hmm.
Thanks.
Later in the course, are you going to talk about kind of quantum analogs and Markov categories?
No, and it will not be part. there's some reason to that, which is, so there has been, most of the work that we have been doing is on the side of somehow classical Markov categories, which try to kind of describe classical probability theory. There are also works that attempt to generalize this framework in a way that includes also quantum probability, and it is possible. So there are some works about quantum Markov categories, and then some variants, involutive Markov categories, and so on. As far as like I and us working on these things are concerned, so far the works on the quantum generalizations have not really nailed the right definition, and that's why I will not be presenting it, because it will be kind of presenting something that we don't think is the ultimate, the right notion. And I mean, I would say it is probably, it's kind of open question for me, like to what extent the framework can be generalized to quantum theory. There is definitely possible in some way, but the question is that a useful way? And I think right now we don't know enough to be able to answer that. So unfortunately, I will not be talking about that, because I didn't feel comfortable presenting something that I don't really believe in. So, okay, now when we have two morphisms, we can compose them together whenever, if the output of F coincides or has the same type as the input of G, then we can plug them in, and in a categorical language that corresponds to just composition of morphisms. In the concrete examples that we have, in discrete probability, we consider the conditional probabilities for F and G, and then we sum over the intermediate outcome. So this, you could see this as a matrix multiplication of the two stochastic matrices. Well, in the measure theoretic case, we have to integrate over the intermediate space.
Yeah, this is what I would call Chapman.
This is the Chapman-Kolmogorov equation, indeed. Yeah.
Thank you.
That's right.
And this is not related to the extension.
No, the Kolmogorov extension theorem is about looking at countably infinite product of sample spaces. So that's a bit different context here. Besides the sequential composition, for any two morphisms, we can also look at the parallel composition. So just placing them side by side. And this expresses the idea, rather than taking two probabilistic processes and composing them in sequence, we compose them in parallel independently. And so just like the independence of distributions, we can express the joint probability, the joint conditional probability, just as a product of the individual conditional probability distributions, and very similarly for the Markov kernels.
Okay,
yeah.
Quick credit, can you go back one slide? Can I express in the continuous variable case, I could, if I wanted to talk about probability densities, say like F tilde is probability density, so F tilde of B given A. Like, are you committed to a certain formalism for the continuous variables in terms of like what your integrals are, and can I kind of use probability densities instead, or am I going to get in trouble if I do that?
For nice spaces, it's going to be equivalent. You might get some different results when you go beyond kind of like nice measurable spaces. And yeah, this is like a piece of the structure that's not really so well understood yet, is the connection between basically what's known as Radon-Nikodym theorem. So that's a way to like take a measure and construct somehow the differential, which gives you the density. I think we have some kind of concept that go in that direction, but like a category, like a Markov category expression of Radon-Nikodym theorem, we don't have yet. So that's.
Thank you.
Yeah. Okay, parallel composition, we talked about that. Now,
Actually, could I
yeah.
ask one question
Yeah, yeah.
about the radon-Nikodym theory?
Yeah.
So, like if you have a Haar measure, if this is like the real line or a group, and you have like, you could just say dB as the Haar measure, and everything works nicely. And my impression has been that radon-Nikodym theory sort of needs that, the Haar measure to be like the denominator of your densities. And
as far as I mean, I'm not an expert on this, so take what I say with a grain of salt. As far as I know, what you need is like absolute continuity condition. So it doesn't have to be Haar measure somehow invariant under some action of a group. What you need is somehow weaker condition, which is, yeah, absolute continuity, I think. Absolutely. And probably Haar measure kind of ensures that, like, it somehow is a stronger condition that you need. Yeah, I think.
Okay, and that somehow convinces you that there is some measure that all the densities you care about are proportional to, because that's the existence of that density function.
I think what I meant is that for nice measurable spaces, you have a concept of a uniform measure, like a Lebesgue measure. And then if you do everything in terms of kind of densities with respect to the Lebesgue measure, then that's going to be equivalent. But there are spaces where you don't have the equivalent of a Lebesgue measure.
Oh, so you're saying the Lebesgue measure is a perfectly good denominator for the radon?
Yes, because actually, as far as measurability is concerned, I will get to this a bit later, but maybe I can like. So, if you look at the particularly nice measurable spaces, then all continuous.
Lebesgue is nice.
Yeah, like so all continuous spaces are going to be measurably isomorphic to the real line. So not topologically isomorphic, so they will have different topology, but as measurable spaces, they're going to be isomorphic. And so you can then do everything in terms of Lebesgue measure. If you only care about the measurability properties, then if you care about topology and other stuff, then not. But
locally, it's like a group.
Yeah.
Essentially.
Yeah.
Okay. Cool.
Okay, I think that's somehow a long introduction to the diagrams, but I hope that, that allows us to then understand the more complicated concepts easier by going kind of a bit slower through all the elements. In particular, so now when we look at the Bayes theorem, we can understand the equation on the right, hopefully. So on the left-hand side, we have some joint state on A and B, and the statement says that we can express the joint state by looking at the marginal, so that's this Q with marginalized on B, and then considering the output A, and on B we just compute some conditional probability of B given A. And so the product comes from the basically considering the composite but not marginalizing over A. So there would be kind of summing over the intermediate space. When we consider A, then we don't sum over the intermediate. Okay, so those are the basic elements of the diagrammatic language. But I said that we don't just have diagrammatic language, but it's also meant to be formal or mathematically precise. And this is what Markov category gives us. So a Markov category is somehow a formal way to kind of underpin the diagrams so that diagrams make sense. And in particular, that if you look at two diagrams, that you can move around the elements of the diagram by basically like maybe moving the morphisms up and down or swapping wires and stuff like that, then that doesn't change the identity of the diagram. So diagrams are kind of like invariant under like topological manipulations. Okay, I don't want to go into the details of the definition. Of course, if you are interested, I can kind of tell you more. For me, the main main message is that the diagrams kind of make sense in the intuitive way as we expect. But technically, indeed, as Rob was saying, so this is going to be a symmetric monoidal category. That means it has these two types of composition, like basic composition, and then the parallel composition, which we also call tensor product, but we don't have to think of it as the tensor product that we know. It's more like a generalized parallel composition. And there is this unit object, I, which is the unit of the monoidal product. So if we take a product of any object in the category with I, then it's going to be isomorphic to the original object. And on top of that, somehow two-dimensional compositional structure, we have these copying and discarding morphisms. And so in general, I have to say, like, what these copying and discarding, they have to satisfy some properties in order for us to be able to interpret them as copying and discarding, basically. And so this is what Roberto was asking. So we have some compatibility conditions between copying and discarding. So if we first copy and then we discard either of the outputs, that's the same as just doing nothing. That's the same as identity. If we can always swap the outputs of the copy, and then it's the same as just copying. We have the associativity. So if we first copy and then copy the left output, is the same as copying the right output after. And also some compatibility between the parallel compositions and copying. So if we want to copy a tensor product of two objects, it's the same as copying the individual objects and then taking the parallel composite of the morphisms. So this is kind of the rules that you can use to manipulate the diagrams, right? So these equations tell you that you can kind of manipulate the diagrams using these rules. And that gives us a kind of way to reason diagrammatically about. Yeah. The last condition that we have is the normalization condition, which says that if we have a morphism and then we marginalize the output, that's the same as just marginalizing the input. And so in the concrete examples that we have been looking at, this says this equation, for example, in the discrete probability case, corresponds to the normalization of the stochastic matrices is that if we sum over the output outcomes, then we get 1 for any input.
It's like trace preserving.
It's trace preserving condition indeed, yeah. So you can consider an alternative version of the theory where you drop this equation and there are going to be some differences. But for many purposes, actually, it's nice to assume this equation, and then a lot of things then simplify in some sense.
Could you explain what I was again?
Yeah, I is an object of the category, so it's kind of like A or B, a wire. But it has this property that it's the unit of the parallel composite. So in the discrete case, it's just a singleton, or in classical probability theory, it's the singleton set, the trivial space.
It is the singleton set. Okay. But it's different from dot. So is the bulk dot? So how is I related to discarding?
To the discarding. So I is the output of the discarding. Yeah.
Okay.
Yeah. Thanks. Okay, we are nearing. Okay, we started a bit later, but we are nearing 1 hour. I will go a little bit, and then we can have a small break. I think this is where I wanted to get to, like the definition, but now I also want to tell you what are the concrete instances of this structure. So one of the concrete Markov categories that we have already seen is called Finn-Stoch. And this, in some sense, is like an easy example and often the one that we use also in our work to motivate or to get new ideas of what we could try to prove. In this case, the objects, which we can think of as just wires, are finite sets. The morphisms are stochastic matrices. We have already seen that. Matrix multiplication gives us sequential composition, and the Kronecker product of the matrices gives us the parallel composition. So just element-wise product. One example is this stochastic matrix. So any column has to sum to 1. That's the normalization condition. Mm-hmm.
Yeah. In Finstock, you also have other morphisms from any things to I, right? Which are, for instance, asking what's the probability of a particular value of
right. So this would not be element of a Finstock. Okay. In Finstock, there is a unique morphism from any object to I, and that's the discarding.
Because those are not normalization.
Exactly. Those are not normalized.
Okay.
But indeed, if you drop the normalization condition, then you can express that, and then you would have something like subnormalized probability distributions, and yeah.
And then would you still have a Markov category, or this would be a different?
It would be called something else. So usually when people drop this last condition, they call it the CD category, copy discard category.
Okay.
That's the name that seems to be stuck. Yeah. And a lot of the theory of Markov categories also extends to CD categories, but usually there is some modification that you have to do to account for the normalization factors.
Yeah.
Yeah. Mm-hmm. Okay, so that's Finstock. There is a variant of Finstock where we also consider negative probabilities. So the objects are the same, but now the stochastic matrices are not valued in the unit interval, but any real number. We still have the same compositional structure, but now we can have negative probabilities, so to say, but we still require that each column sums to 1. So the normalization is still there. This, I wouldn't say that's a particularly important example in terms of its interpretation, or like, I mean, one could discuss that, but the main interest in this example for me is that it can often offer counterexamples to some conjectures, or is a kind of very similar to Finstock, but it has a lot of different structural properties. Finset multi, on the other hand, I think can be quite nice. So this is a category where we still have finite sets, but the stochastic matrices are now just valued in the 0, 1, the set of either false or true. So that's we can also think of it as a Boolean semiring of true and false values. And when we think of it as a matrix, then it's still the same compositional structure. And the stochastic matrix is now 0, 1 valued, where if we sum each column, it should be 1, where, of course, sum is just going to give you the minimum in this case. And so that's why the normalization condition just says that at least one of the elements should be 1. At least one element should be possible, because this category, you can think of it as a kind of possibilistic version of Finstock, where you only care about what's possible, what's impossible. Mm-hmm.
Back to plus minus.
Yeah.
This might be a little out there. Have you thought about C-star algebras?
Mm-hmm. We'll get there.
Okay, and so do you have in mind, so, you know, you've relaxed positivity, and a lot of the time you have like a convolution structure around. So this is very close to being an involutive Banach algebra.
Mm-hmm.
Yeah, and so you're going to comment a little on, so I really like involutive Banach algebras,
okay,
and how they're almost C-star algebras, except they're missing the C-star property.
Yeah.
And it's interesting how you can have a new kind of positivity, even if the numbers are literally not positive. So you might say something about that.
I might say something about that. I don't think, I was not planning to go into detail of this, but of course, like, we can also talk like outside of the lectures more about that. Yeah, I think in the interest of time, I'll continue, but yeah, feel free to talk to me about it.
So you're sympathetic to some of what I said.
Yeah.
Oh, great.
But I would say also this framework gives at least some kind of insight on this question. So it's a good question. Yeah. Okay, so there's the possibilistic case. Now yeah, I said that they are matrices, but we can also think of them as multi-valued function, and then the composition is just relational composition. That's just an alternative way to think of the same structure. And in fact, so the 3 examples I gave you so far, they all look quite similar, and there is a kind of general version that corresponds, that thinks of finite sets as objects, and somehow stochastic matrices valued now in some commutative semiring R, and in fact it can be any commutative semiring, and then you get matrix multiplication and product as the composites, and in a commutative semiring you can always like sum, so we have the normalization condition. And for example, I know one example that's different from the previous 3 is if you consider the semiring of just like 2 Z2s, two Boolean semirings as a direct sum, then you can have also somehow alternative versions, but there are many others. Some are quite wacky in a way, and these can often be like very nice like playground for thinking about counterexamples to various conjectures. So often we will be thinking about like axioms for Markov categories, and sometimes you have one axiom that implies the other, and to show that the opposite implication is not true, often we have used this kind of Markov categories because based on the properties of the semiring, you will either have or not have different properties of the Markov category.
Often it is just a ring. That's just a ring, right? Or that's, you call it a semi-ring, but I'm using all these inverses in my head. Is that so a lot of the time?
I mean, it's not always, because I mean, for example, in Finstoch, we don't have additive inverses.
But often you do think of the semi-ring as a full ring.
I think if I would say that Finstoch is kind of like one of the most basic examples, then actually no. Yeah.
Okay.
I think. Yeah.
What did KL of DR?
Or sorry, of course, Finstoch has multiplicative inverses, right?
Oh, I don't know.
Yeah.
I can only retain so much.
Yeah. So going to the multiplicative inverses, so we in classical probability theory we often divide, right? So we assume that we have inverses of scalars, and I think this is an interesting point, that in this language we generally cannot divide, and so that's why we have the semiring structure that's kind of the more basic one. And if you wanted to divide, then you would have to add additional elements to the language of the Markov category. So I think it's actually an important kind of subtlety, is that if you want to express some statement in classical probability theory that has division, you have to first like massage it into a form that does not involve division and then translate it, like the Bayes theorem. So Bayes theorem you could see as dividing the joint probability with the marginal probability, and that you cannot express in Markov category, but if you multiply by the marginal, then you can. And so in some sense, one of the lessons of this work is that you can do a lot without having to divide probabilities.
Oh, sure.
Maybe not everything, but there's a lot that you can do with just this structure.
If I could just, so where I was coming from is I think a lot about convolutions, and those usually have inverses in them, and I can't actually tell if that notion of a ring and having inverses is related to what you're saying here. I just sort of assumed they were. So it illuminates it all why.
Yeah, I'm not sure actually.
This thing about
Convolution is something that we have not thought about much. So it might be an interesting next step at some point. Yeah. Okay, let's. Do you have a question?
It's like the Kleisli
Kleisli category. So
distributions of R's.
indeed. So yeah, you can think of it as the category of finite sets and functions. Then you look at the distribution monad valued in R over that, and then the Kleisli category is the Markov category.
What is that word, KL? Would you say it again?
It's a kind of categorical notion where you can take one category together with like way of adding structure to its objects and then construct a new category out of it. So the structure on objects here is basically the structure of probability distributions valued in R. And given that structure, so that's this dr, you can construct the Kleisli category. So Kleisli is a name. And the Kleisli category is then the category of morphisms with outputs in that structured object. So in the space of probability distributions. That's like a general way to construct Markov categories also. So, but this is like a lot of category theory that I don't want to go into the details of here. Okay, so now the measure theory. So this we already also have seen. So in the continuous case, we can consider some kind of nice measurable spaces which up to isomorphism are going to be discrete spaces, the countables, like natural numbers, or a continuous one, so there will be, let's say, real numbers up to isomorphism that's unique. Then the morphisms are Markov kernels, we have already seen that. The Chapman-Kolmogorov equation for sequential composition, and again, just taking products for parallel composition. There is another version which is still a Markov category. If you drop the niceness of the measurable spaces, you get the category stock of arbitrary measurable spaces. And this can be also interesting to consider. Often it has not so many nice properties because you don't consider nice measurable spaces. But it still works, and it still actually has some nice properties. It's just not enough for us to be able to prove a lot of the stuff that we want. You can consider a topological version where you look at somehow topological spaces, could be compact Hausdorff, could be actually also more general. Then you look at Markov kernels, where now instead of the measurability condition, you have continuity for the Markov kernels. You can still integrate over these topological spaces. So it's very similar, but you replace measurability by continuity. And a very related one is the category where you consider the algebraic perspective, where now, okay, so this is like quite a complicated name for it, but I mean, there's some reason for it, but it's not so important why. The objects are then commutative C-star algebras. And now, pay attention, that the morphisms between the objects are going to be, okay, some positive and unital linear maps in the opposite direction. Okay, so when we look at the algebraic perspective, that's, I mean, for like quantum-minded people, that's like taking the Heisenberg picture, and so the linear maps are going in the opposite direction. Okay, when we look at the sequential composition, then we have the composition of the linear maps, but in opposite order, of course, and tensor product is just tensor product, which in the commutative case is going to be unique. In non-commutative case, you would have different tensor products, but we don't consider non-commutative. The unit element of the monoidal product is the one-dimensional algebra, so just complex numbers. And now this is also something interesting, perhaps, or something to note, that when you have this perspective in the opposite direction, in the algebraic perspective, then the copying is just multiplication of the multiplication in the algebra. Okay. Yeah. And the deletion, well, deletion now is going to be mapped from the trivial algebra to some other algebra, and it just is the linear map that takes the one to the identity in that algebra.
Can you go over the copy business? I didn't follow that.
Yeah. Let's think about it. So copying is going to be a linear map from 2 copies of A to 1 copy of A.
So you're talking about the adjunctive copy.
Yeah. So this bar is the kind of the linear representation of the morphism.
Got it. Yeah. Okay. Yeah.
So I can think about sort of these, commutative C-star algebras are just continuous functions or
On Hausdorff spaces.
Hausdorff spaces.
Compact Hausdorff, yeah.
Those would be kind of probability density functions in the
Density. Which one?
the morphisms, let's say a state.
There's a question in the exercise sheet about that, but yes, basically, not quite densities, but there would be some kind of measures, yeah, or Markov kernels. In fact, if you know the Gelfand duality, then this category is very much related to this category. I think so. I would expect that there are actually isomorphic S Markov categories, but I never checked that, so maybe I shouldn't say that. But yeah, they are very much related to each other. Yeah. Do I have more examples? Let me see. No, that's all the examples I have for now, and I think I will end there for today. And I think now we've kind of concluded the introduction, and tomorrow we will look at somehow additional things that we can, additional concepts and additional properties that we can define, and with like the idea in mind that we want to somehow reason about these Markov categories and derive some non-trivial results. So yeah. Rob?
Just a comment, you mentioned dropping the kind of trace preserving axiom and getting to a copy discard category rather than a Markov category. It seems to me that's probably related to what John and David and I do in our causal inferential theories, where we look at a category of substochastic matrices.
Mm-hmm.
And what's particularly nice about that is that you can then have Boolean propositional logic encoded in the category.
Mm-hmm.
So, normally we think about dropping that, to be able to deal with unnormalized distributions, but there's actually a much greater payoff, which is that if you think of sort of like a theory of inference should include Boolean propositional logic, and to do that, you can just move to this slightly more general thing.
Yeah, so, yeah, that's very much true. Like Roberto was saying, like if we have morphisms, like from A, so these are morphisms from A to the unit, which are not the discarding, but are propositions, basically. So if these are somehow deterministic, then they would be propositions. If they are stochastic, then they could be also like stochastic proposition. But then we can use the Markov category structure to look at, for example, this proposition, which would then be the end. Yeah. The or is not there, but I mean you could then add it.
Yeah, I mean in our paper we show how you define the or and the not and all that.
Yeah.
It all lives inside this.
Yeah, I mean I would say that's a very, I think that's a very nice, very natural extension of the language, which, yeah, definitely if you want to do certain things, you will need it. You will need to go beyond like just normalized morphisms. Yeah, I think there are many variants actually. So you can drop the normalization, but you can also drop other, or like generalize other properties. For example, in the recent paper on law of large numbers, which I will hopefully get to in the last lecture, there we need to drop somehow the fact that all of these stochastic matrices are defined everywhere. They're kind of like stochastic matrix that's defined for every input. But if you want to express the fact that, for example, like not every sequence, or not every infinite sequence of outcomes has like a well-defined like limiting empirical distribution, like relative frequencies that they don't converge, then the construction of like these limiting relative frequencies is not a morphism in this category because it's not well defined somewhere. And so then we can drop the fact that this morphism should be well defined everywhere, and we have kind of partial morphisms So that's also useful sometimes. There's other variants, I would say, that can be useful. And yeah, I think the interaction of the propositional logic and the kind of uncertainty reasoning is important.
Yeah.
Yeah.
The way we did it, we had an object which was kind of just a Boolean true or false.
Mhm.
Does that ever show up in any of these?
That would be going into the topos direction. We have not used it or needed it for anything. So far, no. But there are other perspectives on this which people in Oxford have been thinking about. So Sam Staton and his group, and they take kind of perspective from coalgebra. So this is a branch of mathematics and category theory, you could say. And there often you work with this Boolean kind of Boolean proposition, like the Boolean semiring that because you can use that to construct other objects as well. Like if you take, it's like looking at coins and like throwing coins as kind of the source, basic source of uncertainty, and constructing other uncertainty out of it. Yeah. Yeah.
You mentioned the Gelfand duality between this and the last one. So I think I'm looking for that word Banach, and so in the last one you've got Hausdorff.
Mm.
Are you good at this stuff? Do you know the relation between Banach spaces and Hausdorff spaces? Like, is that Banach property just there? And do you know what I'm asking?
I'm not sure.
Would you show your Hausdorff slide?
Yes.
So when I think of the Gelfand dual
Yeah.
commutative C-star algebra, I'm looking for a certain kind of Banach space. And so I'm like, okay, this probably is a Banach space.
Yes.
But I just don't see the word Banach.
Banach space. What is Banach space?
Banach just means it has a norm, and maybe the assumption that, so then that Banach space just always is Hausdorff. Like, I guess everything has a norm, so, right, everything is, just being able to say something is stochastic means it has a norm.
Well, I guess like how's
It's a Banach space, isn't it?
yeah, but it's a different norm.
The Gelfand representation of a Banach space, I thought. What were you saying? Sorry.
Yeah, I mean, I agree with Tyne that like the C-star algebra is also a Banach algebra with the C identity, right? Or Banach star algebra together with the C-star identity. But I mean, on this side, like if you have a topological space that's metrizable, like I guess Hausdorff spaces are metrizable if I remember correctly from my undergrad, then you have a metric and then you can use that to define a norm. But well, okay, you need to at least be able to. I'm not sure. Yeah. Not sure. Yeah.
Maybe you're going to get to this when we do more constructions.
Mm-hmm.
But thinking from a categorical point of view, is there anything you can say about like what limits or co-limits this category does or doesn't have for a general Markov category?
In general, no. I mean, no, not in general, but it is a very important categorical structure. I mean, this gives us somehow, if we assume, or if we can prove that particular Markov categories have certain shaped limits and colimits, then that gives us a lot of things to work with. And indeed, like a lot of the kind of nice properties that I will be talking about can be expressed as universal properties of the Markov category.
Cool.
Thanks very much.
Thank you. Okay. Thank you. See you tomorrow.